Thank you, Chris. Okay, let's get started with talking network performance. We have only 25 minutes, so I'll start quickly with a very short introduction. My name is Arjan Schaaf. I tried to pronounce it in English, it won't work. Arjan Schaaf. I work for a company called Luminous. It's founded in the Netherlands, but we work around Europe, and our customer base is both in Europe and the United States. Over the last few years, we developed what we call the Amdatu PaaS software stack to modularly develop software. And we also needed hosting to make it a full PaaS, and that's how we ended up with containers. We run our deployments both in the public and the private cloud, and we try to be a cloud provider independent. We started out with Amazon, but a lot of our customers also have a need for public clouds like Azure or their own private cloud. So the Cloud RTI is founded on the usual suspects in this room. We use CoreOS, Docker, Kubernetes more and more, and it offers things like load balancing and access to data stores in the Elk stack. And we use it, and our customers use it to develop high available, scalable applications with software components like centralized logging and monitoring and metrics. So starting with clouds, like I mentioned, we started out with AWS, and customers felt the need for Azure. So I thought, how hard can it be? And our software is ready for it. Let's run our stuff on a different cloud. And the first setups we created, we had a real issue with performance, and I didn't know who to blame. Was it Azure? Was it the SDN we were using at the moment, Weave, or was the problem in our own code? We needed some tests to isolate the problem, and that's what my talk is about. Let's go over the virtual machines I tried to use in this performance test. I made a subset of the available virtual machines on Azure and AWS. Your choices are a lot wider than what's on this slide, but we tried to select a couple of the tiny instances. That's the A series 0 and 1 on Azure, and their counterparts, both in price and on paper on performance, are the T2 family micro and medium instances. And for a more generic performance type, we use the newer D series on Azure, and the latest generic performance family, the M4 instances on AWS. And to see if money buys good performance, we tried a couple of the bigger instances as well. If you look at the network performance, both Azure and AWS are pretty fake about how their virtual machines perform. Microsoft doesn't provide any information on their specification pages. I found the performance on the A series on a slide somewhere on the internet by a Microsoft partner. I'm not sure even if these numbers are accurate. No information about the D series, and if you look at the higher end A8, Microsoft does tell you proudly that they offer an infinity band network connection. And AWS more or less does the same thing. It talks in stuff like low to moderate performance or moderate high, and at the higher end they tell you you got full access to a 10 gigabit connection. So how did we approach these network tests? Well, we started out with a cool tool called QPerf. You see it often in discussions on the internet and blog posts, and it's a real simple tool to do a short running network test between two nodes. But I got some results out of that tool that often indicated quite different numbers after repeated runs that I couldn't explain. So I tried some other tools out, and I ended up using the iPerf tool as well. Also a long-running tool. It's currently in the third generation with a new version recently released, and we use that to create some longer running tests with a high number of parallel connections, because it's one thing to have your network connection saturated with just one connection, but for our use cases, it's also very important to know how your network connection performs when you have a lot of parallel connections running at the same time. If you want to try these tests on your own environment, or try to make sure that I did my test correctly, I made the containers that are used in these tests available on the Docker Hub. To start with kubeperf, we first are going to run a server on a host, and it's a pretty simple Docker command to get the server started. You register a couple of ports and tell it to listen on port 4000 in this example. And after that, you can launch a client container on a second host, and it only needs to know the IP address of the server, and we tell the client which test suites to run. So in this example, I'm running both a TCP bandwidth test and a latency test. Looking at the iPerf tool, it looks kind of similar. I start a server by telling it to run in server mode, and I'm going to connect a client to that server. And in the first example, I'm testing what I call the native network bandwidth, but that's not really native because I'm still using containers, but we are connecting the two containers over the host interface. So there's no software-defined network in between the two containers. And then we got these results. So in blue we have the kubeperf, and in in gray we have the iPerf results. And well, first thing to notice is the high performance of the largest Amazon instance. We're actually saturating the 10 gigabit network connection in these tests. And the other thing to notice is that the A8 should be 4 times as quick, but somehow it isn't. Probably my setup with CoreOS and the default settings, I didn't tweak anything to do with the network's connections. By far doesn't maximize the results of the theoretical 40 gigabit connection on that machine. Let's discard the highest value and zoom into the other results. Two things I noticed. The Azure machines more or less give the same results using kubeperf and iPerf. And somehow the Amazon machines have a hard time dealing with the 128 simultaneously connections that are running in the iPerf test. I think this might be explainable by that Azure is really throttling your network connection. So the virtual machine itself should get higher results if Microsoft wasn't throttling your bandwidth. The other test we ran was latency, and well, it's kind of obvious. The results of Amazon are a lot better than similar machines on Azure. So Amazon is doing a better job here. But like I said, I wasn't sure if Azure was the only problem we were facing, or that the software-defined network was also causing some performance problems. So let's continue on to repeating these tests, but then using the Docker networking. So you've got a couple of options. If you want to connect containers over the network in Docker, the basic connection was where I started with. You register a port on the host machine, and you connect the containers through the host interface. If you do that, please consider using ambassadors to make configuration a bit simpler, but you probably need a more advanced approach if you get a bigger cluster running a lot of hosts with an even higher number of the Docker containers. So I think you're going to want to use a software-defined network. There are a lot of options. I'll be discussing three today: Weave, Flannel, and Calico. Before Docker 1.7, how you would configure your SDN all depended on the implementation. Some provided a replacement Docker bridge. Some recommended not to do that, like Weave. They have a good blog post on their website why you shouldn't use Weave as a Docker bridge. So Weave fortunately offers another solution as well in the form of a proxy that runs in front of the Docker daemon. If we look at the future, with the announcement of Docker 1.7, they also announced an experimental channel where you can try out new features that didn't make the public release yet. And the first feature they announced was libnetwork. And libnetwork provides a way to hook network plugins into your Docker daemon. And they provide a included battery. In this case, it's a socket plane, which was bought by Docker. You can also use one of the other plugins, like the ones announced by Weave and Calico and other parties like Cisco and VMware. Which would make it a lot easier to get the or the setup right. You still need to configure the settings for the different solutions, but you won't have the challenge that you might end up with a configuration that's not recommended by the plugin provider. Which is great because then we can choose an SDN on stuff that really matters, like features offered. An SDN like Weave offers extra functionality compared to something like Flannel, like DNS and encryption of your network traffic. But also you might be interested in the actual support for libnetwork. Flannel doesn't yet support libnetwork or stuff like Kubernetes. So apart from the functionality, it's good to know that these implementations of the various SDNs can differ quite a lot. Flannel and Weave are both overlay networks on top of the network you already running in your cloud. But they use different backends. For example, Flannel uses UDP. Calico has a completely different approach. It's a layer 2-3 network-based network. I'll discuss that later on in a bit more details. So if we first look at Flannel, created by CoreOS, so it's really easy to set up if you use CoreOS, and it provides different backends. I'll show you some results of the UDP and the VXLAN based implementation, but you could also use on a couple of the public clouds the routing tables provided by that cloud, which in theory should result in lower overhead on your own virtual machines. For this demo, I used the 1.0 release of Weave. 1.1 was released earlier this week. I haven't had the time to see if it makes any difference. Like I already said, it provides other functionality like DNS, and it's based around a proxy. The current release has a PK-based implementation, but they're working on a VXLAN-based implementation. It's available in preview mode, and I heard here that they are trying to release the VXLAN-based solution as soon as possible, which is a good thing, as I will show you later on. Calico takes a whole different approach. It's based on the same principles used on the internet with BGP routes, and it specifically should work really well in a data center setup where you have access to the layer 2 and 3 of the network, which isn't the case on a public cloud like AWS. You need an additional tunnel, so it will become kind of an overlay network in the end on the public cloud. Cool thing about Calico is the potential integration with Kubernetes and stuff like the network policies they offer, which should allow you to, for example, isolate tenants in a multi-tenant setup. So onto the test setup we used to test the SDNs. It's basically the same test like the first one I showed, but instead of using the IP address of the host, I'm using the IP address or the DNS name provided by the software-defined network to the container. And if we look at the charts now, again, we notice the N for 10 extra large. Flannel in the UDP implementation, which uses the user space, is pretty low, but the VXLAN is almost as good as the native performance. Weave is lagging, and Calico as well, a bit as well. If we zoom into the other instances, you notice that, the results out of Flannel, both implementations are pretty close, and Weave is catching up with some of the virtual machines, but on the higher end, it's a bit behind. If we zoom in on the iPerf results, especially the mid-size virtual machines, we see a different picture. Somehow all the different implementations, or at least Flannel and Weave, get very close results, and all very close to the native performance results, which are the light blue bars. Calico is still a bit behind in some of the results. Let's look at the latency really quick. Pretty decent, except Weave is a bit disappointing maybe. But let's focus on the bandwidth for now, and let's compare the native with the SDN performance. What I noticed was that the tiniest and the biggest virtual machines, they have quite some differences. The big one is probably explainable by the configuration of the network stack. We, for example, wrote a blog on how to get the maximum performance using their technology on 10 gigabit connections. You need to tweak the MTU sizes. But when we look at the mid-size virtual machines, they're all really close. So it's hard to choose just based on the performance, right? If we focus on the mid-size virtual machines. So let's throw in something else, namely the CPU load. Those are a lot of numbers, but I compared both the client side and the server side with the actual performance. And if we simplify this table, then we get the following table, and it compares the CPU overhead with the native CPU load. And what we notice then is that the Flannel UDP load is quite high. On the client side, it uses twice the CPU load than the native one. A bit less on the server side, but Flannel using the VXLAN approach gets a lot of better results, and that's probably just due to the fact that the kernel can take care of the VXLAN approach a lot more efficient than the user space approach. The Weave results are not so good. I would love to get my hands on the new implementation of Weave, and I'll blog about it when that version is available. And let's hope that it's up there with the Flannel VXLAN implementation. Calico, yeah, well, it's again sort of in the middle. So, yeah, what to choose? Just based on performance, and performance isn't the only thing. Of course, you might also choose technology like Weave for the functionality it offers, or Calico could also have different criteria to make your selection on. For now, we are running Flannel VXLAN in production. it suits our needs for now, and we're happy with the low overhead, and it helps us to save money on hosting. However, we are interested in the other projects as well, and we are closely monitoring them. For example, Calico has a really nice integration with upcoming features of Kubernetes. So that might help us out in a multi-tenant Kubernetes-based deployment. And possibly that would put the performance degradation in a different perspective. It's also good to remember that synthetic tests like these are a great starting point, but a synthetic test is a synthetic test. You need to validate the results you're going to get by real-life load tests on your own application, because like I mentioned, we are running with the highest number of parallel connections, possibly in iPerf, but that might not suit your use case. If you need less connections, you're going to see different results. I tried the iPerf on the largest Amazon machine with different sets of connections, and when you use only one connection, you're completely saturating the network connection. So the number of concurrent connections does have an impact on the results you're going to get out of your network. Some links on the topics that we discussed. If you want to know more about the tweaking of the 10 gigabit network connection on Weave, do check their blog. And they also have a couple of other good blogs on how to maximize the performance, like not using the Docker bridge. And I'll keep on blogging about this subject, so keep an eye on my blog if you have an interest in this subject. Thank you.